Let's look at some examples where we are going to solve a separable differential equation or initial value problem. Just to make things easier, I've written down the 4 steps that you can follow, and we'll work through these one by one as we walk through each example. Let's look at our first example. I have labeled this example as basic, and I thought it would be a really good one to start with. The first thing that we're going to do is separate the variables on each side. I'm going to bring the y to the left and the dx to the right. So we have y times dy is equal to x squared times dx. In step 2, what we're going to do is we are going to integrate each side and then add on an arbitrary constant. We're going to have the integral of y dy, and that's equal to the integral of x squared dx. Let's go ahead and integrate this. We have y squared divided by 2 is equal to x cubed divided by 3 plus our constant. And I am going to call this constant C1 because we might have to relabel it later, and I always like to end with our constant being equal to C. I think it makes the solution just look a little bit cleaner. Our third step is to solve for the dependent variable y. I'll highlight y so you can see what we're going to be solving for. So this is step 3. Let's go ahead and multiply by 2 first. This gives us y squared is equal to 2/3 x cubed plus 2 times c1. Now we can go ahead and take the square root and solve for y. Don't forget that we're going to have a plus or minus whenever you take the square root. And inside we have 2/3 x cubed plus 2c1. Now let's look at step 4. Step 4 is that we are going to rename the constant if necessary. Let me highlight our constant here. Our constant is 2c1. I am going to relabel this as c. So in step 4, we can have the nice solution y is equal to plus or minus. We have our square root. And inside we have 2/3 x cubed plus c. And that's our final solution. Let's now look at our second example. This is another basic example, but has a little bit of algebraic simplification in it. And that's pretty common with these types of equations. Our first step is to separate the variables. I am going to take the dx to the right, and I'm going to bring the y to the left. This gives us dy divided by y is equal to x times dx. Our second step is to integrate. We have the integral of 1 over y dy on the left, and we have the integral of x dx on the right. This is the natural log of absolute value y on the left, and on the right we have x squared divided by 2 plus our arbitrary constant, which I'm going to call c1. Our third step is to solve for y. Notice that our y is inside a natural log. The only way to get y out of the natural log is to exponentiate both sides. On the left, we're going to have e to the ln absolute y, and then on the right, we have e to the x squared divided by 2 plus c1. This gives us just the absolute value of y on the left, and on the right, here's what I'm going to do. I want to clean this up a little bit, so I'm going to write this as e to the c1 times e to the x squared over 2. Just remember that e to the a plus b is e to the a times e to the b. That's why I was able to split that up. Now we need to solve for y. It has an absolute value with it. This means that the absolute value of y is plus or minus y. We can bring that plus or minus to the right. And let me go over here so we have space. So this is y is equal to plus or minus e to the c1 times e to the x squared over 2. Now we can go on to step 4, and that is to rename our constant. This expression right here is a constant, and I'm going to call that c. So we get the answer y is equal to c times e to the x squared divided by 2. I think that just makes the answer look a lot nicer. Let's now look at example 3. This is an example where we can only get an implicit solution. I wanted to do one of these so you can see what that really looks like. Our first step is to separate the variables. We'll bring the dx to the right, and then we'll bring this whole expression in the denominator to the left. We'll have to use parentheses. This gives us 2y plus cosine y times dy is equal to 6x squared times dx. Step 2 is to integrate each side and then add on our arbitrary constant. This gives us the integral of 2y plus cosine y times dy is equal to the integral 6x squared dx. Now we can integrate. The integral of 2y is y squared. The integral of cosine is sine. So we have a y squared plus sine y on the left. And then on the right, we can integrate x squared, and that's going to be x cubed over 3. And then we add on an arbitrary constant c1. We can clean up the right-hand side, so I'm going to rewrite this as y squared plus sine y is equal to 2x cubed plus c1. Our third step is to solve for y, but I already kind of told you that we're not going to be able to do that by telling you that we're going to get an implicit solution. If you look at this expression right here, I want you to notice that there's no way to just solve for y. Because of that, I'm going to write down for step 3 that we can't solve for y. And then in step 4, I'm just going to rename this constant right here. This gives our final solution as y squared plus sine y is equal to 2x cubed plus c. And there's our final answer. Notice in this problem, we could have made this c1 just a c to start with, but you never know ahead of time. So I always just say, let's start with c1, just to make it easier if we do have to rename it. Let's now look at example 4. In this example, when we go to integrate, we are going to have to use u substitution. I wanted to put one of these on because I think the hardest thing for students when you're solving differential equations is having to do some of the integration that you learned in calculus 2. Let's start with step 1. We are going to separate the variables. I'm actually going to do this in 2 steps. I'm going to keep the dy on the left, so I have e to the x squared times dy, and on the right I have a minus xy cubed dx. Now I'm going to bring the y cubed to the left and the e to the x squared to the right. This gives us 1 over y cubed times dy, and on the right we have a minus x all over e to the x squared times dx. Because we are going to be integrating in our next step, I am going to rewrite this, and I'm going to rewrite it so we can integrate it easier. This becomes y to the minus 3 dy on the left, and on the right, we have minus x e to the minus x squared dx. Now we can go ahead and step 2, which is to integrate both sides. We have the integral y to the minus 3 dy is equal to the integral minus x e to the minus x squared dx. Let's go ahead and integrate the left-hand side. Remember, when you integrate, you take your constant. Let me highlight that. We have a negative 3 there. We're going to add 1 and then divide by what we get. This becomes y to the minus 3 plus 1, so that's y to the minus 2, all divided by minus 2, equal to, and then this right-hand side is a little bit more complicated. So I'm just going to put dot, 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 and we're going to come over here and solve this one. To integrate this function, we are going to have to use u substitution. This is going to be our u, and we're choosing that because our du is minus 2x dx, and we have the minus x dx in our integral. We let u equal minus x squared, and then du is minus 2x dx. We can then notice that on our right-hand side, I just talked about this, but I'm going to highlight it now. We have a minus x dx, so I'm going to solve for that. So minus x dx is du all divided by 2. Now we could substitute in our u and our minus x dx. This gives us the integral of e to the u times du over 2. The integral of e to the u is just e to the u, so we have 1/2 e to the u, and then we'll add on our c1. Let's bring this down. We now have minus 1 over 2y squared. Notice that I rewrote that to make it a little bit easier. And then we have 1/2 e to the u, but now we're going to replace u with minus x squared. And then we have our c1. Let's now move on to step 3. Step 3 is to solve for y. We definitely can with this one. I think what I'm going to do first is multiply by minus 2. This gives us 1 over y squared. Let's give us some more space. Remember, we're multiplying by minus 2 on both sides. So this gives us a minus e to the minus x squared minus 2c1. Now to solve for y, we are just going to take both sides and we're going to take the inverse. This gives us y squared on the left, and then on the right, I'm going to write it as 1 all divided by minus e to the minus x squared minus 2c1. Now we can solve for y by taking the square root. This gives us y is equal to, remember, you take the square root, you need that plus or minus. We have 1 all divided by minus e to the minus x squared minus 2c1. For step 4, we are going to make our answer look better, and we are going to rename our constant. If we go over here to the right, I am going to call minus 2c1 c. So our answer is going to be y is equal to plus or minus. We have our square root, and I'm going to write these in reverse order, just so our positive term comes first. This gives us 1 all divided by c minus e to the minus x squared. And there's our final answer, and that is written in the simplest, cleanest form. Let's look at example 5. This is our last example, and it's by far our hardest. I wanted to include this because when we do our integration, we are going to have to use partial fractions. If I were saying this in class, I would hear a lot of moans right now. But don't worry, I'll walk you through it, and it won't be too painful. I also wanted to include this because this is called an initial value problem. That's because we are given what's called an initial condition. And whenever we have one of these, we don't end up with an arbitrary constant. Instead, we end up with what's called a particular solution. Let's go ahead and start. Our first step is to separate our variables. I'm going to take the dy on the left, and I'm going to divide by y minus y squared. So we have 1 over y minus y squared times dy, and that's equal to dx. Now we can go ahead and integrate. Here's where our partial fractions are going to come in. The only way to integrate this expression is to use partial fractions. Let's go ahead and set that up. We take what's inside our integral, 1 over y minus y squared, and we have to break it up. We're going to factor the denominator, so we pull out a y, and that leaves us with 1 minus y. Both of those are linear factors, so we can split it up as a divided by y plus b divided by 1 minus y. Now what we have to do, and this might seem a little strange, we have to pull it back together. So we're going to make a denominator y times 1 minus y, and you can think of cross multiplying. So this becomes a times 1 minus y plus b times y. Now what we're going to do is we're going to set 1 equal to this expression. Let's do that. We have 1 equals a times 1 minus y plus b times y. There are actually two ways that are common to go about solving this. I'm going to show you the first way, and then I'll show you another way. The first way is we go ahead and multiply everything out on the right-hand side. So we get 1 is equal to a minus ay plus by. Then we're going to combine like terms. So we have 1 is equal to a plus y times minus a plus b. Right where we are now is where students typically stumble. What I always tell my students to do is on the left-hand side, rewrite it as 0 times y plus 1. And then on the right-hand side, everything stays the same. Now we can set 0 equal to minus a plus b, and we can set 1 equal to a. Let's do that. We have 0 is minus a plus b, and 1 is equal to a. If we plug this right up into here, we get 0 is equal to minus 1 plus b, and that tells us that b is equal to 1. So we have our solution. A is 1 and b is 1. Let me now show you another way to do this, and I think this way is a little bit easier. Let's go back up to this line, and I am going to look at the 1 minus y and the y. We're going to take the 1 minus y, set it equal to 0. That gives us y is equal to 1. And then we're going to take our expression. I'll just rewrite it here just so you can see what we're doing. We're going to plug in y is equal to 1. So we're going to end up with 1. 1 minus 1 is 0. Y is 1, so we just get b. And now we have our b is 1. Now we do the same thing for the y term. We're going to set y equal to 0. I'm looking right back up here. And then up here, we're going to let y be equal to 0. So we have 1 is equal to a. And then the b multiplies 0 and goes away. And we get a is 1. Now we can go ahead and do our integration. Let's go back up here for a minute and let's plug this in. So we got that a and b are both 1. So this is 1 over y plus 1 over 1 minus y. That's what we're going to be integrating. We have the integral 1 over y plus 1 over 1 minus y dy. And on our right-hand side, we just had dx. Now we can integrate. This is natural log absolute value y plus natural log absolute value 1 minus y. And we're going to have to multiply it by a negative 1 because the derivative of minus y is minus 1. And our right-hand side is just x, and then we add on our arbitrary constant c1. Let me rewrite this. This is natural log absolute y minus natural log absolute 1 minus y is equal to x plus c1. We're going to need a formula, so let me just write it over here. I don't know if you remember this or not, but natural log a minus natural log b is the natural log of a divided by b. We're going to use this because it's going to enable us to eventually solve for y. Our left-hand side now becomes natural log absolute value y divided by 1 minus y, and our right-hand side stays the same. Our third step is to solve for y. We need to get our y's out of the natural log, so we are going to have to exponentiate each side. This gives us e to the natural log y over 1 minus y is equal to e to the x plus c1. On the left, we have y over 1 minus y. I'm going to try to write more neat. It looks like it was getting pretty messy there. And our right-hand side, I'm going to rewrite this. Here's another formula we have to use. E to the a plus b is e to the a times e to the b. So I'm going to rewrite our right-hand side as e. I just noticed we needed a c1 there. So e to the c1 times e to the x. Now we want to get rid of the absolute value. So we're going to have plus or minus. I'm going to pull that over to the right. This gives us plus or minus e to the c1 times e to the x. I am going to make this equal to c2. I'm not going to make it equal to c yet because I don't know if there's going to be other changes still to come. This becomes c2 e to the x. Hang with me. I know this is a long problem, but that happens when you study differential equations. These problems get pretty long. I am going to take this expression and pull it over to the next page. We have y over 1 minus y is equal to c2 times e to the x. Now we need to solve for y. So what we're going to do is we're going to take this denominator and we're going to multiply both sides by that. So we have y is equal to c2 e to the x times 1 minus y. We want to solve for y, so let's distribute what's on our right-hand side. This gives us c2 e to the x minus c2 e to the x times y. Now we can pull this term to the left, and we have y plus c2 e to the xy is equal to c2 e to the x. We can pull out a y, and we're left with 1 plus c2 e to the x, and our right-hand side stays the same. Now we can go ahead and solve for y. We are getting close. c2 e to the x, all divided by 1 plus c2 e to the x. Our fourth step is to rewrite our constant. I am going to call c2 c. This becomes c e to the x, all divided by 1 plus c e to the x. This is called our general solution. Remember though, with this problem, we were given an initial value. That initial value was that y at 0 is equal to 2. So what we're doing with this initial value is we're picking out one particular solution. So we are going to let x be equal to 0 and y be equal to 2, and we're going to find c. This gives us 2 on the left, and then we have c times e to the 0, all divided by 1 plus c times e to the 0. E to the 0 is 1, so this is c over 1 plus c. Now we need to solve for c. We're going to take this and multiply it by 2. So we have 2 times 1 plus c is equal to c. Let's distribute the 2. 2 plus 2c is equal to c. And that gives us that c is equal to minus 2. Let's highlight that. We are almost done. All we have to do now is we just have to go back up to this equation for y and substitute in that c is equal to minus 2. We have y is equal to minus 2 e to the x, all divided by 1 minus 2 e to the x. And that is our final solution, and that's called a particular solution. And that's it. You now know how to identify and solve separable differential equations by separating the variables, integrating each side, and solving for the dependent variable if possible. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.